Hello, everyone. I know you're looking like, what is that? So I typed up some notes. I wanted to show, so we're starting section 4.5, and I wanted to show the concept behind what we're doing, and some things, the theory behind it might be a little too much to show right now, but it isn't too bad, and hopefully you'll follow the algebra, and once you understand it, then we won't have to go through this process again. But I do want to show you the process so you understand sort of everything we do, and I think this is a better way to understand. I know some students, you all have come to me asking me about strategies in terms of studying for this class. Definitely reading ahead will help. I can't mention that enough. Reading ahead, even if you don't understand, reading ahead in the book will help you, because when you come to class, or now when you see these video notes, you'll be like, oh, that's what that meant in the book, right? And so I would advise you to sort of read in the book this section before even looking at this video, to hopefully to bring clarity to what you're reading in the book. Okay. And in the book, they started talking about linear first order DEs. And I skipped that part in the notes because we know the different methods, and they're just showing you sort of in terms of using variation of parameters, how to apply it and how it's understood in that realm. But we have so many different ways to look at our linear first order DEs that I'm not going to spend time going over that, although you can read it in your book. So I'm actually starting with linear second order DEs. And so remember in 4.4, we talked about, we have that table, right, that you should copy in your notes. You need to copy that table in your notes about the particular solution and practice forming them. They shouldn't be too difficult. The only issue comes into play if your complementary function is a duplicate when you look at the right side of the function, right? And you have to be a little careful there. But nevertheless, we are moving on. So now in section 4.5, if you want to stop the video and write this down, let me advise you too, for those of you that do notes on your tablet or in things, that you might take a snapshot of this and then just keep writing or not write it at all. It is beneficial, and there's actually research that talks about how actually handwriting your notes versus typing them or even doing them on your iPad, it helps you retain better. Okay. And I actually, when I'm doing my notes, I do them by hand first. So even if they're typed, or even if I have them, on my iPad, I actually write them out by hand first. Not all the time, but those concepts or those things I want to make sure that I convey clearly, I write it out by hand first, and it helps me to hopefully help you all understand it better. But okay, so now to the notes. We will, so again, pause the video and write this down. But here's the thing. So we've looked at this before, and now g of x, remember in 4.4, g of x can only be certain things, right? It can be sine or cosine, it can be a linear, quadratic, but it can't be like 1 over x, it can't be log, and things of that nature. And so variation of parameters is sort of like, and when I was going through my notes, I thought of it analogously to the quadratic formula. So you know how most of you all love the quadratic formula, of course, insert sarcasm, right? But no, you know that you sort of use quadratic formula if all else fails, sort of, if you can't factor right away, if the AC method doesn't work, if factor by grouping doesn't work, when you have this quadratic, then you use quadratic formula. So variation of parameter will always work no matter what this is. So even in those exercises you've done in 4.4, you can use this method as well. But in particular, it widens our scope because now we're able to tackle those g of x functions that might not be in our nice list that we have to follow in 4.4. Okay. All right. So let's get started finally. So let's consider, we started, like I said, a second order. So let's consider this second order DE, right? Well, the first thing we need to do is divide everything by a sub 2. Okay. And so when we do that, we'll get this equation here in 6, y double prime, plus p of x y prime plus q of x y equals f of x, where of course, since we divided by a sub 2, these are what p, q, and f represent, right? We're assuming that they're continuous on some interval, okay? And you may have to state what interval that is, so you just look to see what the domain is of each of those functions and state where it's continuous, okay? So we know how to approach for second order. So y of c will get, we know how to find the complementary function, right? That's the solution to the homogeneous equation. And so for second order, it's going to be in the form y of c equals c1 times y1 of x plus c2 times y2, right? Assuming the coefficients in 6 are constants, right? So we're assuming that the coefficients in 6 are constant, okay? And I'm using 6 because this is what's in your book, and I just wanted to align it to what's in your book. And so here is, in terms of what we're going to do for variation of parameters, and that should be such, so that word should be such that over there. If we replace C1 and C2, so you know how we usually state constants there. What if we replace those with functions? Okay, u sub 1 and u sub 2, all right? And in fact, we will then have what we call a particular solution. And I don't know why I'm using this that yellow. So we'll have this y of p. Our particular solution is going to be u of 1 times y plus u of 2 times y sub 2. Okay, u sub 2 times y sub 2. And this is going to be a particular solution of this right here. Okay, so now our goal is, how do we find these functions u of 1 and u of 2? U sub 1 and U sub 2. Okay. And so again, you can pause the video here, but the setup is very similar to what we're used to, right? So we have, again, we're looking at, I don't have that equation. So again, we're looking at this equation 6 over here, right? And we're going to say, well, y sub p, our particular solution is u sub 1, y sub 1 plus u sub 2, y sub 2, right? Well, if we take that derivative, what'll happen? It's product rule, okay? I won't go through all that, but some people use the derivative of second times the first. I use that, and I might have stated in another video, but I use it this way just because it's easier to remember quotient rule, right? Because product rule, addition is commutative, so we're okay either way. But with quotient rule, we have to be careful because subtraction is not commutative, right? And so for quotient rule, you have to take the derivative of the top times the derivative of the bottom minus the derivative of the bottom times the derivative of the top. So for me, it's just easier to remember if I do this format, but it's up to you. And then yp double prime. Here you have to be careful. If you wrote this down already, if you didn't write this down, I will pause the video. Just make sure you're getting the same answers that I'm getting here. But here we have yp double prime. Okay. And so again, looking at 6, we're plugging in. So y double prime will just stay the same, right? And then y prime, we will multiply all those terms by p. And then y is just going to be multiplied by q. And so here is our end result here. Okay. And I didn't write everything down because I wanted, us to have fun together doing this, of course. So let's see. Let's break this down. Yes. Okay. So here is and this is where it gets a little tricky, and I'm not expecting you all to see this. Again, I want you to understand and hopefully understand the algebra and the math behind it, but I wouldn't expect you to just bring certain terms together that need to be together. All right. But this is going to help us solve our variation of parameters and solve our u sub 1 and u sub 2 functions. All right, so here we go. So since y sub 1 and y sub 2 satisfies the homogeneous equation, what I'm going to do is regroup these terms. And this is how I'm going to regroup them. So I'm not changing anything. I'm just regrouping. So I'm going to factor out a u sub 1. And if I do that, I'll get y sub 1 double prime plus p y sub 1 prime plus q y sub 1. Okay, and of course I'm looking at my notes right now, so I'm not just automatically looking there. I'm looking at my notes because I've written this down already. Plus y sub 2. And what will y sub 2 be inside? Well, y sub 2 double prime plus py sub 2 prime plus q y sub 2. Okay. And then we'll still be left with, let's see, plus u sub 1 prime y sub 1 prime plus u sub 1 prime y sub 1 prime, and I'm not putting them together for a reason, plus p u sub 1 prime y sub 1 plus u sub 1 double prime y sub 1 plus u sub 2 prime u sub 2 prime y sub 2 prime plus u sub 2 prime y sub 2 prime plus p u sub 2 prime y sub 2 plus u sub 2 double prime y sub 2. And I hope my u's and my w's, u's and y's aren't getting confused. But here's what's going on. Here's what I want you to see that's pretty cool. The reason why I grouped this together is because this right here, this is y sub 1, right? And if we go back and look at 6, so maybe you might want to rewrite that on that page. If you go back and look at that, y sub 1, remember y sub 1 and y sub 2 are solutions to the homogeneous equation, right? They're solutions to the homogeneous equation. Well, what that means is this will go to 0, and also this term will go to 0, because that's representing, if I plugged in y sub 1, right? If I plugged in y sub 1, if we look again at, okay, so I rewrote it on this page so we wouldn't have to keep flipping back and forth. But here, again, that's the solution to the homogeneous equation. So that goes to 0. And this, because y sub 1 and y sub 2 are the functions, right? Those are the functions that satisfy the homogeneous equation. So therefore, those go to 0. So what we have is this. Okay, so we have this here. And I regrouped them. And I regrouped them for a reason. And so here, so you can pause and write this down, this line right here with the yellow, with the now purple arrow is, because the first two, so because these two, right, they went to 0, so they're gone. So we're now left with the remaining terms, but I restructured them in a way so you guys can see something. And this is what I want you to see. So write that down and make sure you agree with me in terms of what's left over, although it might look, the formatting and the position of it might look different. But here's what's even nicer. This right here is the product rule if we were to take the product of u1 prime y1, right? Because it's u double prime times y1 plus y prime times u1 prime. That is so cool. Okay. And then here is the derivative using the product rule of u2 prime y2. Okay. And then we're left with p of, I'm going to write it as u1 prime y1 plus u2 prime y2, and then plus u1 prime y1 prime plus u2 prime y2 prime. And I'm going to have to go to the next page, but hopefully you all will still be on the same page. So because we're not done yet. But again, I just want you, hopefully you follow the algebra and the logic behind what we're doing, because it'll help you better grasp the problems and understand when you're doing the problems. And I see we're almost out of time. I don't like going over 15 minutes, but let's finish. I do want to finish this. Okay. So we're back, and all I did now was put, by rules of derivatives, I put those two together. And so it became the derivative of u1 prime y1 plus u2 prime y2. Okay, that's all. That's just properties of derivatives. And then the other terms stayed the same. Now I added, this is going to equal f of x. And so what we want to do, what this method does is tell us, well, not tell us, but so again, it shows, well, our goal is again to find u sub 1 and y and u sub 2, right? We're trying to find those functions. So here's the thing. Notice that these two are the same, right? Well, so if we get u sub 1 prime y sub 1 plus u sub 2 prime y sub 2, if we say we want that to equal 0, then that's going to force u sub 1 prime y sub 1 prime plus u sub 2 prime y sub 2 prime to equal f of x. Okay, and we use Cramer's rule to express the solution in terms of determinants. Okay. And we're going to stop here. If you have not had linear algebra, it's okay. We've talked about determinants. So Cramer's rule is going to be really nice. It's a really nice, straightforward rule. And I'm going to stop this video here and we're going to continue, and then I'll do an example and then we'll be done with the notes.